Good morning, everyone. It is a great pleasure to welcome you all to the Global Water Futures Core Modeling webinar series. My name is Praveen Rokaya. I'm the Science Coordinator of the Core Modeling and Forecasting team, and I want to thank you all for joining us today, despite many online meetings and webinars that we have these days. So we really appreciate your engagement. Today we have Professor Philip von Kapellen from the University of Waterloo, who will be presenting on the advances in water quality modeling. It will be about 45 minutes of presentation, followed by 15 minutes of question and answer session. Before we begin, I wanted to share that next month on 1st of April, we'll be having Professor Al Petronero from the University of Calgary, who will be presenting on advances in hydrological forecasting. So please stay tuned. Today, I'm very pleased to introduce Professor Philip von Kapellen. Philip is a Canada Excellence Research Chair Laureate in Ecohydrology. In core modeling, he is the faculty lead of the water quality modeling team. This team is working to understand historical water quality trends, to develop, benchmark, and apply process-based nutrient models, and improve water quality algorithms with an aim to improve predictive water quality modeling from sub-watershed to continental scale, which I believe Philip will be highlighting today. Philip, we are very happy and grateful to have you here today, and the floor is yours.
Thank you, Praveen. So before we get started, I'd like to first acknowledge that I'm speaking to you from the traditional territory of the neutral Anishinaabe and Haudenosaunee people. And I'm talking to you from my home, which is situated on the Haldimand Tract. That's the land that was promised to the Six Nations of the Grand River. So I'd like everybody to take a moment and acknowledge and appreciate the enduring role of Indigenous peoples as stewards of our shared land and water. And on this occasion in particular, also as stewards of the quality of our water resources. So let me first start by introducing now the water quality core modeling team. So on the left-hand side, the list is the list of the current and two former postdoctoral fellows and associate researchers that form the core modeling, the water quality core modeling team. So we have Zara, Eric, Sergey, Suyata, Yogo, Luca, Mehdi, Homa, Julie, and Bifikadu. And the stars for Sergey and Homa indicate that they're no longer formally member of the water quality core modeling. They now have different appointments, but they're actually continuing the same work that they did when they were part of the water quality core modeling, and I'll show some of their research results also. On the right-hand side, you see some of the more senior people that are acting as supervisors or are closely involved with the activities of the water quality core modeling. And I'd also like to acknowledge, of course, Prabin, who has been helping with the logistics of coordinating the different meetings and keeping track of also the progress of the team as a whole. So what I'd like to do today is to maybe start off with a little bit of a background on water quality modeling. So kind of what are the general challenges that we have when we want to model water quality of freshwater systems. And then I'll spend most of the time giving an overview of the water quality modeling activities within the team. So we'll see applications of existing water quality models, but also comparative and performance analysis of these existing models that sometimes, and I'll show you at least one example where this actually leads to upgrading an existing water quality model. There will also be entirely new model developments. Obviously, a big topic in the team is how do you essentially couple water quality calculations with hydrological and hydrodynamic simulations. And I'll speak a little bit about water quality data analysis. And I'll finish by giving at least a personal view of what some of the future directions and opportunities are within this field, but also particularly as it relates to the core modeling team. I want to also provide you with a disclaimer. What I will be presenting is not an exhaustive overview of all the water quality modeling work within Global Water Futures. There's other projects that are not directly supported by this team, but that are doing some very exciting, some very new water quality modeling. And even within what is going on within the team, given the limited time, I will obviously skim over some of the realizations or some of the activities. And so I apologize for that. But I hope at least that this overview will give you an idea of the capacity that's available in water quality modeling within the team. And you should feel free as a GWF researcher to reach out to our team for support in your own research. I hope that at least this update will also allow us to stimulate that type of discussion. And so when I present different projects, on each of the slides, you will see the name of the person who is doing that work. And so feel free to reach out to that person, or you can also reach out to me or to Prabin to help you direct to that particular expertise that you might require in your research. But let me first start by essentially asking the question, what is water quality? And maybe I should have done this as a poll and ask all the participants here, how would you define water quality? And of course, there's not a unique definition of water quality. And so here, for instance, is one that is from the United States Geological Survey, from the USGS. It says water quality can be thought of as a measure of the suitability of water for a particular use based on selected physical, chemical, and biological characteristics. To determine water quality, scientists first measure and analyze characteristics of the water, such as temperature, dissolved mineral content, and number of bacteria. Selected characteristics are then compared to numeric standards and guidelines to decide if the water is suitable for a particular use. So you can see this is a very, what I would call a utilitarian view of water quality. So it starts from the end use of the water and then defines what the appropriate water quality is. But you can still see that it's relatively, to a certain extent, kind of vague, because it starts up and you can think of water quality as a measure of, etc. So it's not as simple as saying, well, what is going to be the water level in Lake Huron next year, given some hydrological predictions. So when you have to explain, or when I try to explain water quality to maybe a more general public, I use what's often used nowadays is the, oops, trouble moving forward here. Looks like here. So water quality is an attempt to keep the water swimmable, fishable, and drinkable. So this is kind of more from the human perspective, I would say. You can also take a more ecological or ecosystem perspective. Here, for instance, is a very nice diagram where you look at the, if you can see my pointer here, you look at the lake, you look at the various human activities in the watershed of the lake that leads to soil erosion, pollution, habitat modification, species introduction. Then these drivers then have certain impacts or have responses of the lake, for instance, in terms of increasing turbidity or increasing nutrients, development of anoxia, which then lead to certain ecological impacts that might affect, for instance, the biodiversity, can cause algal blooms, etc. So what you see is that there's different perspectives on water quality. And so one way to then reconcile the human perspective or the societal perspective and ecosystem perspective is through concepts such as ecosystem services. So really start dealing with water quality as a socio-ecological parameter. So then how do we measure water quality? Again, it depends on who you are, what your interest is, or for which agency you're working, or also what your expertise is. And so here you see the list of typical water quality measurements: temperature, salinity, turbidity, pH, major ion composition, things like hardness, the biological oxygen demand, redox potential, or defining redox conditions in terms of the availability of electron donors and acceptors, dissolved organic carbon, and the list goes on and on and on. And so that obviously also points to the problem of saying, well, we are water quality modelers. Well, what kind of variables are you considering? And obviously there's no water quality model in the world that will essentially simulate all these different variables. Now, at the very base or the theoretical basis of, I would say, essentially most environmental models are so-called the conservation equation. So the conservation of energy, of momentum, and of mass. And when most of the project that you will see that I'll present from the core team deal with certain chemical characteristics, well, not always chemical characteristics, but also temperature, chemical characteristics of a water system, a hydro system. And so, for instance, if we talk about temperature, obviously we're talking about conservation of energy and all the processes that can produce or consume heat. Obviously, we're dealing with hydrological systems, so we're of course dependent on being able to say something about the flow of water through our system, whether it's a groundwater or a surface water system, and so we have to then consider conservation of momentum. And then if we're talking about a chemical constituent, then, or even a biological constituents, for instance, bacterial numbers or pathogen numbers, we're dealing with the conservation of mass. And in particular, the equation, the conservation of solute mass here, you see a bunch of terms here on the right-hand side that deal with the mixing and the transport of the constituent. And then you have all these terms, these big R's, which actually reflect to the rates of processes that actually are affecting the constituent in the hydro system of interest. And so these big R's, these rates, are essentially one of the challenges in water quality modeling when we're dealing with reactive constituents, so constituents that actually can undergo transformations in the system of interest. So essentially, to go back to the modeling aspect, to be able to essentially account for the spatial and temporal distribution of a water quality parameter, whether it is temperature, whether it is turbidity, or whether it's a particular chemical constituent, say nitrogen or phosphorus. We need to obviously specify the sources to a particular system, account for the transformation processes in the system, and those could be physical, could be, for instance, a phase transition. It could be chemical processes, say sorption, desorption processes, or mineral formation. They could be biological processes, uptake of a nutrient, for instance, by algae, or mineralization processes. And then the sinks and the outputs could be towards the, for instance, if we're looking at a river, the sink could be the outflow to a lake, but for instance, nitrogen also be denitrification and the release of gaseous nitrogen to the atmosphere. So in terms of now looking at these transformation processes, this is kind of the general scheme then for a water quality modeling, where you account, of course, for the sources of whatever variable you're interested in within the system, which is the big box here. You have to then account for, or you have to have a mathematical representation of the transport and mixing processes, and then account for all the transformations if you're dealing with a reactive constituent. And reactive taken broadly, including also biological constituents of the system. And so I've marked here a couple of these transformation processes. If you're able to come up with mathematical representations for the transport and the transformations, you should be able to then predict or simulate the spatial and temporal distributions, but also particularly for reactive species, also account for the different forms under which, say, for instance, nitrogen occurs in a lake or in a river system. A lot of times when we have these reactive constituents, and again, let's think about nitrogen, you can actually produce byproducts. So for instance, in the process of denitrification, nitrate ultimately is transformed to N2 gas that then can degas to the atmosphere. But you also produce byproducts such, for instance, as nitrite and nitrous oxide. And these byproducts can also have an impact on water quality, and therefore you then also have to account for their transport and transformation processes. And then ultimately you have your sinks. This could be a downstream basin, could be uptake by biota. If you're dealing with an agricultural system, it could be uptake of carbon and nutrients by crops. It could be essentially burial in sediments. And of course, both, well, in fact, and your sources and your system and your sinks are then also subject to external forcings. So this gives you kind of the overall scheme that we're working in. And of course, not a single person within the core modeling team does everything, but it kind of fits within this general framework. So when we talk about reactions, this is kind of a good way to represent them, and it's from Diogo. For instance, he's developed a nitrogen module and a phosphorus module to represent processes in soils in catchments. And it nicely shows with different symbols the sources. So for instance, if you look at the nitrogen module, you have a fertilizer application, plant litter, you have atmospheric deposition. Then the rectangles represent the different pool, the different species, if you want, of nitrogen in the system. And then you also have your sinks. Then here you have your nitrogen module, and here you have your phosphorus module. So if you look at that, you might say, well, I'm really only interested in nitrogen, so I'll just use the nitrogen module, or I'm only interested in the phosphorus module, so I'll just use the phosphorus module. But of course, there are couplings between nitrogen and phosphorus. For instance, if you a lot of experimental and field observation have shown that, for instance, in lakes, if you're looking at, for instance, phosphorus mobility, it actually depends on the availability of nitrate. Low nitrate concentrations tend to enhance the mobility of phosphorus, or the recycling of phosphorus to the lake system. And if the nitrate is too high, you can actually have the opposite effect. So you have also these couplings between your different modules. And so I like to show this one because I can't even read what's on there, but essentially it's a soil biogeochemical module that essentially deals with nitrogen, with carbon, and with sulfur. And you see all these lines going between all these different boxes, which show these couplings between the elemental cycles of sulfur, nitrogen, and carbon in a soil system. And obviously, if you develop one of these very complex, highly coupled reaction networks, you probably can claim that you are more realistically representing what is really happening in natural soil, because we know from experience and from a lot of data that indeed what happens to the carbon is directly linked to what happens to the nitrogen, which is directly linked to what happens here to the sulfur. So you have a more realistic representation of your system. But of course, to run one of these models, you have to specify a lot of different parameters. And most of these parameters are empirical. There's no real theoretical foundation to predict these parameters. So by making your model more accurate in terms of its model structure, by saying, well, my model is more realistic, more closely resembling the real world, you of course are increasing the uncertainty associated with the assignment of all these parameters. So, and that's really the struggle we often have in water quality modeling, is to balance the degree of accuracy or the degree of realism that we want to build into our models versus, of course, the uncertainty that's associated with the representation of all these different processes and the parameterization of all these processes. All right, so let's now look at some of the ongoing projects or finished projects within the core modeling group. We'll talk about soil and snowpack processes, stream temperature modeling, sediment transport modeling, catchment water quality models, reservoirs and nutrient legacies, talk about the watershed-lake linkages, and then finish with some examples of lake modeling work. So as I said in the upcoming, in the upcoming slides, down here we'll always mark the name of the person that is conducting this or carrying out the project. So here we have work from Mehdi, so he works on soils. Really from the perspective that soils are the critical reactive interface between the atmosphere, the terrestrial biosphere, and the hydrosphere. And particularly has been working on the effect of soil moisture and thermal regimes on soil carbon and nutrient cycling, both in natural and agricultural soil. But really, ultimately, from the viewpoint of how is this also going to influence then the stream and groundwater water quality. And the specific interest is, of course, for cold region soils, and so to also take into account processes such as snowmelt, freeze-thaw cycles, other winter processes, and also agricultural practices. And just as an example here, this is the results of a reactive transport modeling project, where Mehdi developed a model to account for the leaching of nitrogen from fertilizer that's applied at the end of the fall by farmers, so that essentially by the time the spring starts, the nutrients would be available for crop uptake. And so this was done under simulated freeze-thaw cycles and freezing of soils also during the winter period, so over a fairly long time period. If you look here at time, it's essentially 2 months. And what it essentially shows here is that even when soils are frozen and when we have freeze-thaw cycles, some of the nitrogen from the fertilizer is actually leaching downwards into the groundwater. And so that, of course, represents an economic cost for the farmer, because essentially that's nitrogen that is not going to be there for the crops in the spring. But of course, it also can have environmental impacts in the downstream rivers and lakes because of eutrophication. So he's also been working at Pore-scale representation of soil carbon, because that's really the drive of most of the processes affecting carbon, nutrients, and other constituents such as metals in soils, and then use upscaling techniques to go from the pore scale to the macroscopic scale, develop constitutive relationships that link soil respiration to soil moisture dynamics. And you see here an example here of CO2 fluxes out of soils as a function of soil moisture, both experimental data and then modeling results. And of course, the soil moisture dynamics are driven by meteorological forcings, but also by things like groundwater fluctuations due to water, groundwater extraction, or farming practices such as tile drainage, etc. Here's some work from Yogo, where he looks at simulating snowpack chemistry. So the idea is that at the end of the winter, when you have a snow melt, what is the chemistry associated with that snow melt? And so if you go to the right-hand side, you have these graphs here. And as a function of time, the envelope here is the snowpack thickness. So you see essentially what you're seeing here is a snow melt event, with also plotted on there chemical concentrations. You have cations such as calcium, magnesium, sodium, potassium, ammonium, chloride, sulfate, nitrate, and protons. And what you see is that in some cases we have significant concentrations, for instance, nitrate, because of atmospheric deposition. To the left-hand side, there you see observations and model calculations of the evolution of the snow melt chemistry. And you can see that there's large variations between the early snow melt versus the late snow melt, with typically the early snow melt being much more concentrated. So we see this whole variation of the chemistry of the snow melt that then ultimately enters into the nearby stream system. Stream temperature modeling, this is work by Luca. So he was interested in figuring out the sensitivity of daily stream temperatures, hydrological configuration versus stream temperature models. So in the mesh surface hydrology model of Environment Canada, to the stream temperature model known as RBM. And so this is a stream, this predicts, or it's based on essentially empirical relationship between headwater temperatures and air temperature. And then he did his analysis using an optimization routine known as Ostrix. And his test case is the Grand River watershed in Ontario. And so what he found in this, that essentially the more sensitive, there's higher sensitivity of his predictions on the stream temperature parameters that are imposed rather than on the hydrology. So in other words, temperature model performance is affected more by the temperature parameters that are supplied to RBM than by the hydrological configuration. The different hydrological configurations he used also have different contributions of surface versus groundwater to the river system. And so that also means that the use of a single hydrological configuration to force large-scale daily stream temperature models is justified. So that, of course, also opens the way to operational forecast of stream water temperature in the mesh model. And sediment transport modeling. Obviously, we're very interested in sediment transport because suspended matter in hydro system is a major carrier of nutrients such as phosphorus, but also contaminants, whether it's metals or hydrophobic organic compounds. If we have the river sediment supply is important for maintaining productive floodplains and sustain river delta habitats, and I'll come back to that in the next few slides. And then a good catchment scale sediment transport model should account for the overland flow, which supplies the sediment to the river system, and then the in-stream transport and processes, and then generate time series of suspended sediment concentrations and loads. And then this type of modeling capacity is important also if we want to inform soil conservation measures, river restoration strategies, or even dam operations, which all are very much influence sediment transport. So the first project here is from Suyata. So she works on the Athabasca River Basin, so a huge river basin, and she has been using mesh again, the Environment Canada modeling platform for surface hydrology, and she has coupled this to the sediment transport model SCD, and so that then results in the mesh SCD. So the equations in the sediment transport model are the classic equations that deal with sediment transport, deposition, suspension, etc. And if you remember what I said about the conservation equations, well, it appears here through the sediment mass balance condition. The model has the capability to account for multiple sediment classes, which is important for future applications on contaminant transport, because different sediment classes have different affinities for different contaminants. And so here are some of her results. So on the left-hand side, you see the calibration using data from 2003 to 2009, and then the validation from 2010 to 2015. And so the blue lines, of course, are the model, the red dots are the data. And so you see this very strong seasonal dependence of sediment transport through the river system here with the high concentration. By the way, the vertical axis here, if you look at the scale, it's a logarithmic scale. So you see order of magnitude higher sediment concentrations or loads. In fact, these are loads here during the summer when we have high flow rates. And then very low during the winter when parts of the river are ice covered and the flow rates are much lower. And of course, the sediment transport or the turbidity seasonal fluctuations in the whole river system are important for the river system itself, but also very important for the Athabasca Delta. And as you probably know, the Athabasca Delta is a biodiversity hotspot, and it's also very important for the livelihood of the indigenous people living in the Delta region. So another sediment transport modeling project is by Eric, and so he's using the WASP model, which is an EPA model, the Water Quality Analysis Simulation Program. It's a program that I think was developed in the early 80s, and then since then has had very many different versions. In particular, they've kept adding sub-models to it. For instance, some that Eric is particularly interested in are the TOXI and the UTRO submodels. TOXI for toxicant transport, fade-in transport, and UTRO for eutrophication. And also, they've also increased the capability to link WASP to other modeling codes. In particular, what is done in Eric's project is to link WASP to Sparrow, so a catchment model, to mesh again, but also particularly for the work that will take place in Lake Diefenbaker, to the SQL2 model, which is a two-dimensional hydrodynamic water quality model. And so his focus is on Lake Diefenbaker, how Lake Diefenbaker dam operations are changing the sediment transport along the South Saskatchewan River. And also of interest in this project is obviously the sediment delivery to the delta of the South Saskatchewan River, which, as you can see on this map, is also important because it is the gateway to Lake Winnipeg. And so at some point it would to, of course, link this work and the sediment delivery through the South Saskatchewan River and the associated nutrients and contaminants to water quality simulations in Lake Winnipeg. A third project is, which was finished actually fairly early on when the core modeling group was started. In fact, we weren't able then, we were still looking for core modelers, so we used some of the financial means to hire some smart students that could help us with the coding. And this is on a much smaller catchment, the Don River catchment. It's about, catchment I think is about close to, well, just under 400 square kilometer. But the notoriety of the Don River is that it's the most urban river in Canada. So its entire watershed is within the Toronto metropolitan area. And if you look at the map, you have some little green spots. That's kind of open areas and green areas, but the kind of light brown to orangey color is essentially all residential areas. So it's a classic example of the urban stream syndrome. Parts of it have been straightened. There's a lot of infrastructure. There's weirs. There's bridges crossing the Don River, and so it's been essentially a problem child for the GRCA, the Toronto, and the TRCA, the Toronto in Region Conservation Authority, and so what we've done then is to couple land use information to an urban hydrology model, the SWIM model, the stormwater management model, which is very important in this case because about 95% of all the stormwater in the catchment is actually straight into the stream. And then couple that to the in-stream hydraulics model, the environmental fluid dynamics code. Also, so those are two EPA models, and then sorption isotherms for copper, lead, and zinc. And so some of the findings, not surprisingly, metal transport is dominated by flooding events. And so you can see this in these CQ relationships. So it's concentration versus discharge. We have these positive relationships. So at high discharge, we have high concentration, high loads of metal. Which also means that most of the metals, a lot of these metals are legacy metals, have now been essentially transported to the lower part of the Don River. And this is a representation of the lower part of the Don River. And we have copper, lead, and zinc. And you can see we have these hotspots where the metals are accumulating. And this information is, of course, important because it tells us that's where cleanup of the river system should take place, rather than waiting until it ends up in the Toronto Harbor, where dredging is much more complicated and costly. All right, so now I've already shown you several projects where existing models are used or existing models are coupled. So of course, it means that there is a lot of catchment scale models with water quality capabilities out there. And so an interesting study that was done by Diogo also early on was to say, okay, let's look at all the available models and let's compare their capabilities. What functionalities are represented in some of the models and not of the other models. And of course, with an interest particularly of how well are they in representing or accounting for the processes that are particularly important in cold regions. So here, for instance, here are the different models that have been compared by Diogo, HYPE, the HSPF, so that's the HPS and for the hydrological simulation program in Fortran, then the integrated catchment model, the INCA model, the SWAT model, the soil and water assessment tool, and then the ANA GNPS is a model that's specifically designed for agricultural watersheds. And so what you see in this figure here, this is for the hydrology. So you go around the circle here, and you have all these different processes that are obviously very important in cold regions hydrology. For instance, snow accumulation, sublimation, snowfall, erosion of frozen soil sublayers, rain on snow, etc., etc. And then the colors indicate whether the corresponding model actually has these processes, these factors represented in their code. And you can see that there's even certain processes like wind redistribution of snow or the erosion of frozen soil layers that are not represented in any of these models. And in some cases, just one or two models represent a particular process. And in some cases, like soil temperature, it's represented in all these different models. What the analysis also does is to identify whether the processes are represented by physically based or more sophisticated process representation, or whether they're empirical or somewhere in between. And so the analysis is also applied to, for instance, in this case, nitrogen species and nitrogen cycling. Again, looking at the different models for, do they represent these different nitrogen species, and do they represent the processes that control the cycling of, in this case, nitrogen. And you can see that only one model, the HSPF, is actually representing all these different nitrogen species and the different processes. So this, of course, helps you guide choosing a model for a particular application you're interested in, but it also offers, of course, opportunities to say, hey, there's a certain, I really like a particular model. I say really like the INCA model, but I also really need to have a better representation of runoff and infiltration in frozen soils. So it offers opportunities to us discovering where we can basically add in or upgrade these models, because most of these models consist have been worked on for a long time. Some of those go back to the 1960s of these models when they were first developed. And so over the years, functionalities can be added to them. So just to look at one example of an upgrading of a catchment model by Befe Kadou. So he worked on HYPE, so it's a semi-distributed hydrology biogeochemistry model. It has a very extensive representation, for instance, of carbon, nitrogen, and phosphorus. But he specifically looked at how HYPE is solving the water fluxes. And in the default HYPE model, it's done sequentially. So essentially, first percolation is calculated, then evapotranspiration is calculated, then horizontal flow is calculated. And what he was able to show is that this sequential approach, which is computationally efficient, may actually yield unrealistic water flux. In particular, under certain conditions, it predicts that there's no horizontal flow. Well, we know that there should be horizontal flow. So to address that, he developed a fully implicit numerical solution, so solving all the equations for these different water fluxes at the same time, which of course gives you the more accurate solution. And particularly, he did that by looking at whether the horizontal flow was predicted under given conditions. but it's computationally much more demanding, and particularly if you want to do a lot of runs, and if you want to run this at a large catchment scale, and you want to look at the carbon, nitrogen, phosphorus at the same time. So then he produced a simplified solution, the LNR3SS solution. And the goal was to essentially have to match the computation efficiency of the sequential solution that's in HYPE, but also to, of course, match the accuracy of the implicit numerical solution. And so here are some results where he compared, for instance, the TP load calculated by the implicit method, so that you can consider the vertical axis here as the true solution, and then compare this to his simplified solution, but also the default HYPE solution. There's also another solution here. But if you just look at the blue and the red symbols, you can see for these are the hourly loads, and these are the daily loads. You could say, well, you have some kind of weird stuff happening here with very high loads predicted by the default HYPE method. But overall, it works kind of okay for the default method, and even get a better match of the one-to-one curve for the simplified solution he developed. But it becomes, particularly if you look at the daily loads, you can see that there's, particularly the high loads, are significantly underrepresented by the default HYPE load. So his conclusion is that obviously more realistic flow paths simulations will yield you more accurate contaminant load estimates, because the load estimates are directly dependent on your flow paths and the flow of water along these different flow paths. It has no extra computational burden compared to default HYPE, and also this solution approach that he presents is also transferable to other hydrological models. Okay, another example is from Diogo, where he is essentially adding water quality modules to modeling platforms that are very suitable for cold temperate regions, in particular the cold regions hydrological model, the CHR-HM, and the mesh model, and then also now working on the SUMA, this new approach, modeling approach that's also being strongly pushed by Martin Clark. So for the moment, he has focused mostly on the macronutrients, nitrogen and phosphorus, and the coupling to these process-based surface hydrology model. And it's also been assessing then, or using this to assess the hydrological connectivity and see how that then translates into the biogeochemical connectivity. So here, for instance, some results from the South Tobacco Creek in Manitoba. And yeah, it works here. You can see that it's a very flashy hydrological system. Sometimes there's certain creeks that are activated, sometimes they're not activated. So essentially, it's a very variable hydrological system. And so what he's been looking at is also then how this hydrological variability translates in the variability in the biogeochemical connectivity. And here you see this biogeochemical connectivity trajectories for 3 different years, and you see that these 3 different years yield very different trajectories. And so capturing this is, of course, a major advance in our understanding how these systems work as biogeochemical flow and transport and reaction systems. Here are some other results from the South Tobacco Creek using the cold regions hydrological model WQ for water quality, which now includes the nitrogen and phosphorus modules. You see here time series for nitrate, ammonia, soluble reactive phosphorus, and particulate phosphorus. And if you look, I mean, you can see that it's a very flashy system, obviously. So you have these events, and for these events, you can see that in some cases, well, there's still some issues here in this, maybe this first event for nitrate and SRP. But what I find interesting is that you can see that the model captures these events where you have N high nitrate, N high ammonia, but also events where you have high ammonia, very little nitrate, and then events like this one where you have high nitrate and low ammonia. So you can see that that biogeochemical, or at least this probably reflects, I think, and that's something that Diogo can talk more knowledgeably about, but this probably means that there's different sources that are activated during these different events, different land-based sources of nitrogen. Okay, then dams and water quality. Just as background information, there are about 15,000 dams in Canada, and about over 1,000 are classified as large, so higher than 15 meters. Obviously, these dams have a lot of beneficial functions. They protect against flooding, ice jamming, they produce hydropower, and they supply water for agricultural and drinking water. Dams also retain suspended sediment, and we've talked already about sediment transport modeling activities, and they also modify the riverine fluxes of carbon nutrients and contaminants. And also many dam reservoirs do experience water quality problems in their reservoirs, in particular eutrophication and algal blooms. So one project on reservoir water quality modeling is by Julie, and she works on Buffalo Lake and Lake Diefenbaker in Saskatchewan, and her work is closely tied to water supply management options that are being considered for Lake Diefenbaker, particularly to augment the water availability for irrigation, but also the water that can then be transferred from Lake Diefenbaker, here's Lake Diefenbaker, to Buffalo Pound down here, this very long kind of reservoir that also supply drinking water to the city of Regina. So the tool she's using is this SQL2. So it's a two-dimensional, 2 stands for two-dimensional hydrodynamics water quality model. And she's exploring different climate change and management scenarios in these two environments in Lake Diefenbaker, but mostly for the moment in Buffalo Pound Lake. Here's, for instance, example where a baseline model, so the kind of, you could think the current situation is compared to one of these water management scenarios, and looking at parameters such as chlorophyll A, phosphate, ammonia, dissolved organic carbon, dissolved oxygen, nitrate, total dissolved solids, and TN. And if you just look at the various curves, for instance, particularly for nitrate here, you see that the large fluctuations in the base scenario are much more attenuated in the one of the proposed management scenarios. So here is a simulation. I'll start it up right away here for one of the basins of Buffalo Pound Lake. You can see it's a very shallow lake. So you see that, so it's temperature, the temperature distributions. You see that we have very little vertical stratification in the pond lake. And what you see is these events, or these wind-driven seiches that basically bounce back and forth from one end of the basin to the other one, keeping it well mixed. So that means that we don't have to worry too much about stratification, thermal stratification in this basin. And thermal stratification is often associated with oxygen depletion in the lower part of a lake or reservoir, and that has a big effect on the internal loading of phosphorus. And yeah, and so that's actually the topic of this second project. It's actually a master's thesis where Zara was providing support. So now we're talking about a Fanshawe Reservoir in Ontario. It's located on the Thames River. Remember that, because I'll continue with the Thames River and Lake St. Clair here in a minute. And it was specifically to look, so Fanshawe is the little reservoir A here. And it was to look at the reservoir effect on riverine phosphorus fluxes and speciation using the same modeling platform SQL2. So here we used extensive data sets that were collected by another of our students over 2018 to 2019. We used the 2018 data to calibrate the model, and then 2019 to validate it. And what I want to point out is that during the summer months, in both years, in 2018, but even more extensively in 2019, we had stratification of the deeper part of the reservoir. So that's the part close to the dam. And so depletion of oxygen, which activates internal phosphorus loading. So during the summer, the reservoir actually acts as a net source of phosphorus to the downstream river reach, so the Thames River, while overall integrated of the entire year, the reservoir actually has net retention of phosphorus. And if you look at the lower graph here, what it shows, so here again is one of these CQ relationships, so the concentration versus discharge relationship. This is often used as a signature of the river and is usually interpreted in terms of the sources of whatever constituent you're interested in, and then the transport pathways from those sources to the river. Now, if you look at the inflow, so this is the river coming in upstream of the reservoir, you have this positive correlation between the concentration of soluble reactive phosphorus and discharge. So this would be called an enrichment trend. But if you do the same, do the measurements in the outflow, in fact, these are all model-derived concentrations, you see that the relationship has completely changed. And in fact, it's more of a chemostatic relationship. So, but rather than saying something or indicating a change in sources of flow paths, essentially this change in the CQ relationship is a signature of the processing of phosphorus in the reservoir. All right, so that's actually brings me, if I go back for a second. So as I said, the reservoir here on an annual basis will retain phosphorus. So phosphorus is accumulating in the reservoir. So this is an example of a legacy that is building up in this case, the stream, but nutrient legacies also build up in the landscape or in the landscape. And so one of the issues that is being addressed, particularly in the research group of Nandita Basu, is how mitigation strategies aimed at reducing nutrient emission of surface waters might be hampered by long-term legacy nutrient inputs. So these legacy nutrient inputs are essentially what is remaining in the landscape over historical time and is slowly released then back to the groundwater or ultimately to the river system. And so in this project, also supported by Zara, was an assessment for the entire province of Ontario of the cumulative phosphorus inputs from 1961 to 2016. And if you look here at the graph here and you see this little counter here, so what you're seeing here is year by year, the what's called the net anthropogenic phosphorus inputs distributed over the entire province of Ontario. And of course, one of the things you see is we have this hotspot of nutrient inputs in the southern part of Ontario, because that's where all the agriculture is taking place, and that's where most of the people in Ontario are living. So the results of that, of course, is that these largest inputs of phosphorus to the landscape are in southwest Ontario. We do see that if you would follow this, we started 64, 65. See the colors are getting redder and redder. So from the 60s to about the late 1970s, we have year by year increasing inputs of phosphorus to the landscape. But since the late 1970s, it's actually decreasing because of increasing crop yields, decreasing livestock, and decreasing urban point sources. But if we look now at the phosphorus loading from Ontario rivers to Lake Erie, so what is carried by the rivers to the lake, it only represents about 12% of the inputs to the watersheds. So it means that about close to 90% of the phosphorus that is brought into the watersheds and applied as fertilizers, as sewage, etc., actually is still staying in the watershed. So we're still building up the legacies. And so now we're coupling these spatial distributions of these phosphorus inputs also to risk mapping of phosphorus export, which of course also depends on the export pathways. Okay, now let's look at, let's get closer to the lakes now and look at the watershed to lake continuum. And the focus here is really on nutrient cycling eutrophication in large lakes, the Laurentian Great Lakes in particular, and also starting now in Lake Winnipeg. And large lakes, of course, have multiple basins. They have complex nearshore offshore exchange dynamics, and the river inputs don't directly go to the offshore lake, but are modulated also by nearshore and interbasin exchange processes. So one project here by Sergey was looking at Lake St. Clair. If I go back here, Lake St. Clair is over here. So it is actually, you have the connection, you have Lake Huron, it's connected then to Lake St. Clair, which then connects to the Detroit River to Lake Erie. And so the Thames River, which is the largest Canadian tributary to the Lake Erie Basin, first enters into Lake St. Clair. And so what Sergey did was to use the Elcom-Kaidem model. So the Elcom model does the 3D hydrodynamics in the lake, and then the KADM is an ecosystem model, and he particularly used the nutrient and phytoplankton components of that model. Lake St. Clair itself is fairly shallow and has a very short residence time, 9 days. But what he was able to show and calculate was not only the whole basin retention of phosphorus in Lake St. Clair, so looking at all the inputs of phosphorus to Lake St. Clair, and then what is actually going out to Lake Erie, to the Detroit River, but also look at tributary-specific phosphorus retentions. And some of his conclusions were that phosphorus retention, it's highly sensitive to resuspension deposition balance because it's a very shallow lake, and thus it depends a lot on the winds, and that can vary, of course, from season to season and from year to year. And in his baseline scenario of 2009, he found a whole basin retention of 17% of total phosphorus and 35% of soluble reactive phosphorus. But the tributary loads, so the loads that are not coming from Lake Huron, those are actually more efficiently retained than the phosphorus load that is coming from Lake Huron. So in other words, in that you can see on this graph here, you see the color here, the blue color. These different colors indicate different percentages of water that is actually delivered from the Thames River. So you can actually follow the phosphorus atoms that are coming from the Thames River, from the other tributaries from Lake Huron, and essentially see how many of the phosphorus atoms delivered by the Thames River actually make it out to Lake Erie. And so you can really, so this gives you a very, very detailed picture of what happens in this Lake St. Clair. Another watershed continuum modeling activity by Zara is to specifically now look at the role of the nearshore zone. And so the zones that you see, or the red color here, is the area that is at water depths less than 15 meters. And of course, the whole western basin is a very shallow basin, so that's all less than 15 meters. And then to try to estimate then how these littoral zones, what is the retention of phosphorus in the littoral zone, but also how do they serve as how are they involved in interchange, interbasin exchanges, sorry. And so this is a much longer time scale than the previous project. So it takes data from 2000 to 2016 to calibrate and parameterize the model. And some of the big conclusions are the load reduction scenarios cause larger change in water column phosphorus concentration in littoral zone. So if we reduce the riverine inputs of phosphorus to the lake, the biggest effect will actually be in these littoral zones and in the Western Basin, less so in the large offshore zones of the Central and Western Basin. But it also shows that there is very significant longshore total phosphorus transport. Now, if we go now to the lake modeling, and so I have a couple more slides here. So again, the focus on large lakes, on phosphorus cycle, on algal productivity, but also particularly on climate change drivers, ice phenology, internal phosphorus loading, and shoreline erosion. We've been using also machine learning techniques to develop algorithms that are trained on satellite data time series like ice phenology, chlorophyll A, and surface temperature. And then the last project I'll show is on phosphorus mass balance modeling. So climate change, so a lot of statistical analysis of time series data, which all show that indeed we have these trends that are indicative of climate warming. So increase in surface water temperatures, also increase in the number of large storm events, and a decrease in ice coverage. And so kind of using this type of data, we can then train algorithms through machine learning techniques to essentially produce predictive relationships. In this particular case, you can see for chlorophyll A. And so those type of predictions are then coming closer to operational predictions of, for instance, algal blooms like the ones that you see here in 2011. Then finally, the phosphorus mass balance modeling for Lake Erie. So this work, and again, I'm sorry, this is very small, but what it really shows, so this is a complete reanalysis of previous estimates, and it really emphasizes the role of interbasin exchanges in terms of understanding how phosphorus is being redistributed in Lake Erie. So again, we have the Western Basin, the Central Basin, and the Eastern Basin. And also it shows very much longshore sediment transport, but also the importance of increasing shoreline erosion as a mechanism to remobilize phosphorus inside the lake. In fact, if you look at these satellite pictures here, you see this kind of suspended matter along the northern shore, for instance, of the Central Basin, and you see it extends down into the Eastern Basin. And actually, this is, we now propose, a major mechanism of total phosphorus transport that is actually increasing because of climate warming induced increases in storm activity that remobilizes suspended matter through shoreline erosion and then pushes it into from one basin to the other basin. All right, so maybe to conclude some thoughts about future directions and opportunities. I think that it's now a good time to look at the various models that we're using, for instance, for nutrients, to do a comparative analysis of how these water quality processes are represented in these different models, whether it's in a watershed, reservoir, or lake models. And also looking particularly also to what degree are some of these reaction networks accounting for the coupling between various water quality parameters. There's certainly scope for further integration and linkages of modeling tools and approaches. For instance, incorporate legacy build-up and export processes in watershed water quality models. So explicitly taking into account that we had historical buildup of legacies that are now still influencing export from the landscape to river systems and ultimately to reservoirs and lakes. linking water quality modeling with ecosystem services or the provision of ecosystem services and economic analysis, such as ecosystem services valuation or cost-benefit analysis for mitigation strategies. Explore also maybe more mechanistic and empirical based approaches, so these machine learning approaches. Model verification at multiple timescales. Very often we look at calibrating and verifying our models for a specific time span, typically on the yearly kind of timescale. But we are usually not fully aware of how well these models will perform, say, on longer timescales. If you go to decadal timescales, particularly if we start thinking about looking at climate scenarios or projected climate change. So maybe also develop within the group, but also in collaboration with other GWF researchers, consistent climate scenarios, so that we all kind of looking forward over the same type of time scales or important time points in the future, and then also in terms of management strategies. We can, of course, further expand the scope of water quality modeling by looking also at additional contaminants of concern, both existing and emerging, to go further into risk mapping and decision support and uncertainty analysis, and then really start addressing also other national and international issues of high importance. Now, of course, given the size of the water quality modeling group, we have to be, of course, strategic. We can't do everything. So I think we really need to start thinking about how to highlight the importance of this work, also to look at issues that are clearly of large interest or a broad interest. And then more closely link also water quality modeling and data management. And for instance, we're working now with DataStream to see how we can better manage and curate and use water quality data. And with that, I'd like to thank everybody who participated in the webinar, and particularly many thanks to all our postdocs and research associates in the water quality core modeling group who essentially did all the work. So thank you very much. And I'm open to questions. Also, some of the more technical questions probably will then be directed or are better directed to the actual core modelers themselves. Thank you.
Thank you, Philip. It was a fantastic and very informative presentation. We'll be now moving towards a Q&A session. We have one question, it's an anonymous question. So the question is, all these research are very great research, but how is that research being applied to improve the water quality in the areas that is being studied? So how the research is actually being translated into the practice?
For instance, I showed the example of the work of Julie Terry in Buffalo Pound Lake. That has very direct implications for which management options will be implemented in the future, or at least we hope that will be. In terms of water quality improvements, for instance, the work that I showed on metal distributions in the Don Valley is actually being considered, or is actually helping directing some of the dredging work in the river, because we've been able to identify where the metals are accumulating. That's not that much so important for the Don River itself. It's more important for the Toronto Harbor, which the International Joint Commission has identified as an area of concern within the Great Lakes. And so it's essentially preventing these metals from entering then that environment. In terms of the lake work, we're, for instance, looking at assessing essentially the potential impact of the proposed reduction in phosphorus loading to Lake Erie by 40%. For instance, what we were able to show, for instance, is that because if you reduce the input of phosphorus from the tributaries to Lake St. Clair by 40%, it actually doesn't translate in a 40% reduction in the total phosphorus that is going from Lake St. Clair to the western basin of Lake Erie, because most of the phosphorus load actually comes from Lake Huron. So I think there's different ways in which we can connect with, of course, practice, and also with essentially informing policy decisions. So it's not that each project has necessarily the same kind of goal in terms of, hey, I want to improve water quality. And it's also it depends on the stakeholders. For instance, the sediment transport work in the South Saskatchewan River Basin is important in terms of hydropower production or hydropower production potential, also in other watersheds. and what it does in terms of sediment starvation in the downstream delta areas. So I think what we're doing is mainly connecting the dots. And as I say here in my last slide, of course, we have to also integrate the different parts of the modeling, but ultimately, we also are a kind of a service-oriented group. So if other projects that have specific end users that want to basically contribute to water quality improvement, they can come to us with specific questions, and we can help them develop or apply the necessary modeling tools to help them, even if they don't have that modeling capability within their own group. So essentially, that's my main message to anyone who says, "Hey, well, I have a water quality issue, but maybe I want to know which model to use." Well, you've seen the comparative analysis of water quality models that already can direct you to the right model to use, and then we might have the expertise in-house to help you implement that particular model in your particular case study.
Thanks.
So it was kind of a long.
Yeah, it's okay. I think we are already 1 minute past the hour mark, so there's 2 more questions. I'll try to frame them in one question, and maybe you can quickly address that. So it's from Mohammad Riaz, and he's wondering if there's any modeling video tutorials, for prospective learners to learn, and if what types of programming skills are needed to require these models.
Well, it really depends on which model, because we go from very simple models to very complex models. So we don't have tutorials as such. Most of the existing models, like whether you have the WASP model or the SWIM model, all those have actually fairly well developed tutorials that you can access online, or they also have manuals that go for it. So mostly what we can do is help you find the manuals that would be necessary. A lot of these models, off-the-shelf models, you don't need to have any programming coding experience. You can use them as a user because the coding has already been done. But I would strongly encourage just to start a conversation with the modeling group, with a specific person or with several persons, and just kind of see what the scope of the issue is, or the system that you are interested in. What kind of, because it often depends on things like, it's not just I want to model, as I started in the beginning, water quality means different things to different people. It also depends on what kind of timescales are you interested in. Do you want to do something, do you want to understand things on a seasonal timescale, on a decadal timescale? All this will kind of determine which kind of the best model to use is. But as I said, there is not a single unique water quality model. That simply doesn't exist. And there's also no real reason for such a model to exist. But it really depends on the question. So you can contact me, you can contact Prabin, so that he can start finding out who would be the best person to talk to. We can also help train students, for instance, in certain modeling capabilities. So I would say, yeah, let's be flexible, but the best is to start talking.
There's a few questions, but I would like to stop here and ask the attendees to email us with the question. And if you can email directly to Philippe or to me, and then I will pass it to Philippe. Thank you again, Philippe. I also want to thank everyone who attended this webinar. And just a reminder that in next month, on 1st of April, we'll be having Professor Al Petronero from the University of Calgary, who will be presenting on advances in hydrological forecasting. So please stay tuned. That will be all for today. Thank you, everyone. Any last comment from you, Philippe?
No, thanks, you. It was a good experience for myself just to assemble all the different projects, and really very impressed by what our postdocs and our core modeling group has been able to achieve in a relatively short amount of time, and with a relatively small group. So I look forward to continue working with all of you. All right.
Thanks again, everyone. I wish you a good day. Bye.
Bye.